Okay, let's unpack this. Picture this scenario. You're apartment hunting in San Francisco, right?
Oh, yeah. Tough market.
Totally. And you walk into a place, it seems.
Uh-huh.
Wh- Okay, but the agent, they tell you there's like a dozen more people coming today.
High pressure.
Exactly. And here's the kicker you have to decide, like right now. Take it or leave it. It's gone.
Wow, that feeling. The what if. The one that got away.
That stone left unturned feeling. Yeah. It sounds familiar to a lot of people, I bet.
It really does. And it's fascinating, that these everyday moments, these decisions under pressure with incomplete info, you can actually look at them through a computer science lens.
Like a human algorithm.
Sort of, yeah.
Yeah.
Designing a strategy and algorithm to navigate these messy parts of life.
Right. And this isn't just like some academic thing. This deep dive, it's all about how computer science can offer, well, surprisingly practical ideas for these challenges.
We're talking concrete strategies.
Yeah, like figuring out when's the best time to, take a leap. Or how do you balance trying new restaurants versus sticking with your favorite?
Even organizing your closet.
Even that, the hidden logic behind it. And the really cool part is a lot of these suggestions aren't just like gut feelings. They often have some serious math backing them up, proofs even.
And it's worth remembering, this isn't just computer science in isolation, just like building computer algorithms pulled from math and engineering.
Right.
Understanding these human algorithms draws from, well, a whole bunch of fields. Computer science, obviously, but also math, stats, operations research.
And the human side.
Oh, definitely.
Yeah.
Cognitive science, psychology, economics. It's really interdisciplinary when you think about it.
Okay, so where should we start our algorithmic adventure? Maybe with those moments where you're facing a sequence of choices.
And saying no means it's gone forever.
Exactly. Like interviewing job candidates, maybe. Or even house hunting, like we said.
That leads us straight into a classic problem, doesn't it? The secretary problem.
Ah, yes, the secretary problem. Explain that framework a bit.
Sure. So imagine you're interviewing, say, a sequence of candidates for one job. After each interview, you have to decide right then, hire this person or move on to the next.
And if you pass on someone.
You can't go back. They're gone. The question is, how do you maximize your chances of picking the single best candidate in the whole pool?
Okay, and this is where it gets kind of weirdly specific, right? The 37% rule.
That's the one. It sounds counterintuitive, but the optimal strategy mathematically is this. You look at and reject the first 37% of the applicants.
Just look and reject. Seems harsh.
Well, this first phase isn't about hiring. It's purely informational. You're setting your baseline, calibrating your expectations, seeing what the field looks like.
Okay, so you get a feel for the quality range. Then what?
Then, after you've seen that first 37%, you hire the very next candidate who is better than everyone you saw in that initial rejection phase.
The first one that beats the benchmark.
Precisely. The look then leap strategy.
And the really wild part is the probability, isn't it?
It is. The probability of finding the single best candidate using this exact strategy is, well, it's about 37%. 1 over E, mathematically.
And that holds true no matter how many candidates there are. 10 or a million.
That's the astonishing part. Roughly 37% probability of success, regardless of the size of the haystack. It's your best defense against an overwhelmingly large number of options.
So even with the perfect strategy, you're still more likely to miss the absolute best one. About 2/3 of the time.
True, if your goal is solely landing the number one pick. But it's the best you can do under those rules. And the bigger the pool, the more valuable this kind of optimal algorithm becomes compared to just guessing.
It makes sense. And speaking of real life, you mentioned an anecdote about someone applying this.
Yeah, Michael Trick. He's an operations research professor now. Back in grad school, he was thinking about dating.
Uh-oh.
And he realized, wait, this is basically the secretary problem. He had a finite window. He figured maybe from age 18 to 40.
So he applied the 37% rule to his dating timeline.
Pretty much. He didn't know exactly how many people he'd date, obviously, but you can apply the rule to time just as easily. He figured the first 37% of that window, roughly until his mid-20s, was his looking phase.
Setting the baseline.
Exactly, establishing his standard. And then he'd be ready to propose to the next person who clearly surpassed everyone he'd met before that point.
And did it work?
Well, the story goes, the first woman he proposed to after that cutoff turned him down.
Oh, no. Classic math meets romance story.
It happens, but it reminds me a bit of Johannes Kepler, the astronomer.
Kepler, what did he do?
After his first wife died, he apparently courted 11 different women. He really liked the fourth one.
Okay, so 4 out of 11. That's around 36%. Close.
But he didn't stop there. He kept looking and eventually chose the fifth woman. But his reasons weren't just about who ranked highest. He considered a broader set of qualities.
Ah, so real life is messier. The criteria aren't always just a simple ranking.
Exactly. The pure secretary problem assumes you can rank everyone relative to each other easily. But our values might shift, and we might weigh different factors as we learn more.
Okay, let's shift gears slightly. Parking. Definitely a common problem. How does optimal stopping apply there?
Our sources look at this interesting scenario. Parking on an infinitely long street where your destination is at a specific point.
Infinitely long. Okay, simplifying assumption.
Right, but the key finding is how much the occupancy rate changes your strategy. If the street is, say, 99% full, really crowded,
Yeah.
the math suggests you should actually drive almost a quarter of a mile past your destination before you even start seriously looking for the first available spot.
Wow, that far. But what if it's less crowded, like 85% full?
Then the optimal point to start looking seriously is much closer, only about half a block past your target. It shows how sensitive the best strategy is to the conditions.
That definitely goes against my usual gut feeling of grabbing the first spot I see near the destination.
It links to real-world work, like Donald Shoup's research on parking, and systems like SF Park in San Francisco, where understanding availability informs pricing and strategy.
Makes sense. Now, what about this burglar problem you mentioned? Sounds intriguing.
It's a great analogy for knowing when to quit while you're ahead. Imagine a burglar having a successful night, hitting several houses.
Okay.
Each successful burglary adds to their haul, but it also increases the cumulative risk of getting caught and losing everything.
The longer they stay out, the higher the chance of getting nabbed.
Exactly. The burglar problem tries to find the optimal stopping point, when should they call it a night, to maximize their expected total loot, balancing potential gain against the rising risk.
It's that tension between greed and fear. Boris Berezovsky, the guy who wrote a book on the secretary problem, probably knew that tension well.
One would imagine so. It's a core trade-off.
So we have these mathematically optimal strategies. But how do actual humans perform? Do we follow the rules?
That's where research like Amnon Rappaport's comes in. He's done decades of experiments on how people tackle secretary-type problems.
And what did he find?
Well, people generally get the basic idea of the look-then-leap rule. They understand setting a standard first.
But
They tend to leap too soon, way too often. In his studies, something like 4/5 of the time, people stopped looking earlier than the optimal 37% point.
impatient.
Seems like it. They still did okay overall, finding a good candidate around 31% of the time, not far off the optimal 37%, but they consistently jumped the gun.
Interesting. Can we illustrate that look-then-leap rule simply? Like with just 3 applicants?
Yeah, the sources use that example. Say you have applicants A, B, and C. The rule says, reject the first one, A. Then, if B is better than A, hire B. If B is not better than A, you must hire C, sight unseen.
Okay. So with 3 applicants, there are 6 possible orders they could arrive in, right?
Yeah.
ABC, ACB, BAC, BCA, CAB, CBA.
Correct. And if you apply that specific reject the first, take the next best rule, it turns out you succeed in finding the absolute best candidate in 3 out of those 6 scenarios.
So a 50% success rate for 3 applicants.
Right. Using that specific strategy, it highlights the core logic, even though the 37% rule is derived for larger numbers.
Okay, that covers when to stop looking. What about the flip side? Balancing trying new things versus sticking with what works. The explore-exploit trade-off.
Yeah, this is a fundamental dilemma. Exploration is all about gathering information, trying that new restaurant, listening to an unfamiliar band, learning a new skill.
Getting data.
Exactly. And exploitation is using the knowledge you already have to get a known, reliable, good result, going back to your favorite restaurant, playing your favorite album, using a skill you've mastered.
It seems obvious that never exploring would be, well, boring, stagnant.
Definitely. You'd miss out on potentially better things, but the sources rightly point out that never exploiting is also bad.
How so?
Think about positive routines, traditions, comfort zones, enjoying time with family, having close long-term friends, savoring your favorite meal. These are all exploitation. They provide reliable satisfaction.
Right, you can't always be searching. You need to enjoy the fruits of your exploration, too.
Precisely. The analogy often used is the multi-armed bandit. Imagine a row of slot machines, each with a different unknown payout probability.
Okay, multiple levers, multiple bandits.
Right. Do you keep pulling the lever on the machine that paid out okay a few times? Exploit. Or do you spend some pulls trying the other machines to see if they might be better in the long run? explore.
Because just a few pulls might not tell you the true payout rate.
Exactly. Early results can be misleading. You need enough data.
And this trade-off isn't just for slot machines or restaurants, is it?
Not at all. The source is connected to all sorts of things. Choosing what movie to watch, sure, but also bigger life stages. Younger people tend to explore more. Older people maybe exploit more established preferences. It also comes up in A/B testing for websites or even clinical trials.
Clinical trials, how?
Well, do doctors stick with the current best treatment, exploit, or try a new experimental one that might be better but carries more uncertainty? Explore. It's a really tough version of the same dilemma.
And these decisions aren't always isolated, right? We face similar choices again and again.
That's a key point. As the mathematician Peter Whittle said, the bandit problem really embodies in essential form a conflict evident in all human action. It's not just about this one choice, but the whole sequence.
So back in our metaphorical casino with the slot machines,
Yep.
which lever should you pull? How do you decide?
It really comes down to one crucial question the sources emphasize. How long are you planning to be in the casino?
Meaning, what's your time horizon? How many more pulls do you get?
Exactly. The optimal balance between explore and exploit depends heavily on how much time or how many opportunities you have left.
So it's not always just carpe diem, seize the day.
Well, seizing the day might mean exploring if you have a long time ahead. But if your time is short, maybe exploiting known good options makes more sense. It complicates the simple, live in the moment idea.
Our sources mention someone who tackled this mathematically, Richard Bellman.
Yes, Bellman looked at the multi-armed bandit problem where you know exactly how many pulls you have in total. His insight was to work backward from the very last pull.
How does working backward help?
On the very last pull, there's no future, so you just pick the option you currently think is best. Knowing that, you can figure out the best strategy for the second to last pull, considering its impact on the last one, and so on, all the way back to the first pull.
Clever. And this led to strategies like the Gittins Index.
Right. The Gittins Index assigns a value to each arm or option. This index represents a kind of guaranteed payout rate that would make you indifferent between taking that guaranteed payout and continuing to play that arm with its uncertainty.
So the strategy is just...
Always play the arm with the highest current Gittins Index. It elegantly balances the potential reward against the uncertainty and remaining time.
And there are other approaches too, like UCB algorithms. Upper confidence bound.
Yeah. UCB algorithms focus on minimizing regret, the difference between what you got and what you could have gotten if you'd known the best option all along.
How do they work?
They look at each option's estimated value, plus a bonus based on how uncertain you are about that estimate. You pick the option with the highest upper confidence bound. This naturally encourages exploring options you haven't tried much, especially early on when uncertainty is high.
Let's go back to clinical trials for a second. That explore-exploit tension seems really acute there.
It absolutely is. There's a real ethical dilemma. Doctors want to give current patients the best known treatment, exploit. But to find better treatments for future patients, they need to run trials with experimental options, explore, which might mean some current patients don't get the current best.
The Belmont Report, which guides medical ethics, acknowledges this, right?
It does. It highlights the tension between benefiting the individual patient and advancing general medical knowledge. Figuring out what constitutes harm versus benefit often requires taking calculated risks through exploration.
And this led to ideas for adaptive trials.
Yes, like Marvin Zellin's play the winner algorithm. It's a way to adjust the trial as it goes based on results.
Play the winner. Sounds intuitive.
It is. If a particular treatment in the trial seems to be working well for patients, the probability of assigning the next patient to that treatment increases. If it's not working, the probability decreases.
So you're learning and adjusting the exploration-exploitation balance within the trial itself.
Exactly. It tries to get more patients onto the seemingly better treatment faster while still gathering data.
It's really striking how these abstract concepts, optimal stopping, explore, exploit, have such deep relevance to incredibly human and sometimes high-stakes decisions.
From finding an apartment to developing new medicines, yeah. The underlying logic is surprisingly similar.
Okay, so we've looked at choosing and balancing options. Let's shift gears now to sorting, organizing things. Seems mundane, maybe.
Maybe at first glance. But the computer science of sorting, as our sources show, has some really fascinating and non-obvious connections to everyday life. Think organizing your office or even understanding social dynamics.
The key insight seems to be about scale.
Yeah, absolutely. Scale hurts. The difficulty, the time it takes to sort things, doesn't just increase linearly, it often explodes as you add more items.
The laundry example is great, doing laundry 3 times as often.
Doesn't just cut the sorting time for each load by 2/3. Because of how sorting complexity scales, it reduces the total sorting effort by a factor of 9. Smaller batches are disproportionately easier to sort.
This is where that big O notation comes in handy.
Precisely. Big O notation is just a shorthand way to describe how the runtime of an algorithm scales with the input size.
Like ON is linear. Double the items, double the time.
Right, like passing a dish around a dinner table. The time is directly proportional to UNT, the number of guests.
And even if you do some huge one-time task first, like remodeling the dining room,
For a large enough N, that initial fixed cost becomes negligible. The ON part dominates.
then you have ON2 quadratic time. Double the items.
Quadruple the time. Things get slow fast.
And ON log N. Linear rhythmic.
That's much better than quadratic. It scales more gracefully, still grows faster than linear, but much, much slower than quadratic, especially for large N.
And the nightmare scenario is ON factorial time.
Yeah, basically impossible for anything more than a handful of items, like trying to sort a deck of cards by repeatedly shuffling it and checking if it's sorted. Don't do that.
So a simple but slow sorting method is bubble sort. That's ON2.
It is. You repeatedly pass through the list, swapping adjacent pairs if they're in the wrong order. Each item bubbles up towards its correct position, but only one step per pass. It's easy to understand, but inefficient for large lists.
Compared to something like merge sort, that's ON log N.
Exactly. Merge sort is a classic divide-and-conquer approach. You split the list in half, recursively sort each half, and then efficiently merge the two sorted halves back together.
And that difference between ON2 and ON log N is huge in practice.
Massive. For a million items, n log n is vastly faster than n squared.
Our sources even mention a real-world sorting machine.
Yeah, the library sorter in Preston, Washington, using barcode scanners and conveyor belts, essentially implementing a physical version of an efficient sorting algorithm like merge sort, sorting 167 books a minute. Impressive automation.
Now, how does sorting relate to, say, sports rankings?
It's a great comparison. Our sources bring up Charles Dodgson Lewis Carroll, who actually analyzed tennis tournaments.
He found problems with single elimination.
He did. He pointed out that in a standard knockout tournament, the probability of the second best player actually winning the second place prize can be surprisingly low. The structure isn't optimized for accurate ranking.
So different tournament formats are like different sorting algorithms.
Kind of. A ladder tournament, where you challenge people above you one by one, is a bit like bubble sort. Slow, takes potentially 0-2 matches to sort everyone out.
Whereas a bracket tournament, like March Madness,
That's much more efficient, structured, like merge sort. It takes only O(n) log n matches to determine a winner.
but leagues don't always use the most efficient ranking method, do they?
Often not. They prioritize other things, like keeping fans engaged, maintaining suspense. Think about MLB's divisional races towards the end of the season. It's designed to keep things interesting, not necessarily to perfectly rank the teams as quickly as possible.
Which leads to the idea of griping rights. How much confidence should we have in these rankings?
Yeah, especially the winner. Sources mention that in sports like baseball, where there's a lot of randomness, even a team with a significantly higher underlying win probability, say 70%, might have a surprisingly low chance, maybe less than 12%, of actually winning a short single elimination tournament. The best team doesn't always win.
So structured tournaments versus something more chaotic like poker.
Right. In cash game poker, there isn't a neat bracket. You're constantly trying to figure out where you stand relative to the others at the table. It's a continuous search-sort trade-off, searching for information about opponents while trying to sort out your own relative skill level to avoid losing your shirt.
Sorting even applies to animals. Pecking orders.
Absolutely. A pecking order in chickens is a social hierarchy, a way of sorting individuals to minimize costly fights over resources. Once the order is established, conflict drops dramatically.
And disrupting that order is bad.
It can be. Studies show that things like debeaking, which might seem to reduce injury, can actually increase overall antagonism because it disrupts the established social sorting. Interestingly, group size also matters. Chickens naturally form flocks of a certain size, and forcing them into much larger groups increases aggression, likely because sorting becomes computationally harder for them.
How do we sort things that seem totally different, like comparing Microsoft and Walmart?
Benchmarks. In business, the benchmark is often money dollars. It provides a common scale to compare wildly different entities. The Silicon Valley saying, "you go to the money," reflects this implicit sorting. It creates a hierarchy that reduces constant jockeying for status.
Okay. From sorting mountains of data or chickens, let's move to managing limited space. Caching. Sounds like a computer thing.
It is fundamental to computers, but the principles, as our sources highlight, apply everywhere. Your brain, your closet, libraries, warehouses, anywhere. You need quick access to some things more than others from a larger set.
So the basic idea is keeping frequently used stuff handy.
Exactly. It's about creating a memory hierarchy. You have a small, fast, easily accessible storage area, the cache, and a larger, slower main storage area. Think of researching in a library. You check out the books you need often and keep them at your desk, the cache, instead of running to the main stack's slow storage every time.
The Atlas supercomputer was an early example.
Yes, one of the first to explicitly use this idea. A fast working memory, cache, and a slower main memory, a magnetic drum. It's about balancing speed, size, and cost.
And how do you decide what stays in the cache and what gets kicked out when it's full?
A very common and often surprisingly effective strategy is least recently used, or LRU.
Least recently used.
Yeah.
Makes
Yep.
sense. If you haven't used something in a while.
It's probably less likely you'll need it again soon compared to something you just used. So when you need to make space, you evict the item that's been gathering dust the longest.
And this is widely used.
Very widely, often in variations. Despite more complex algorithms existing, LRU is simple and works well because the near future often does resemble the recent past in terms of access patterns.
The library example from Berkeley was interesting.
Yeah.
A hidden cache of returned books.
Yeah, they apparently kept recently returned popular books aside for faster reshelving. The sources suggest, hey, why not just put those on a cart in the lobby? Make the cache visible and accessible. That aligns perfectly with the purpose of a cache, quick access to likely needed items.
Caching isn't just about speed, though, right? Amazon warehouses.
Right. There, the scarce resource isn't necessarily processor cycles, but physical proximity and picker travel time. Even in their massive, somewhat randomly organized warehouses, they keep high-demand items in a more easily accessible cache area near the packing stations. It minimizes travel time.
So, once you decide what to keep nearby, how do you organize within that space? Filing versus piling.
We often hear advice like group like with like. But our sources mention Yukio Noguchi's filing system, which seems counterintuitive at first.
What does he do?
He organizes files based solely on when they were last used, with the most recent on one end, or top. It's a physical implementation of LRU.
So, ignoring categories completely.
Essentially, yes, for retrieval purposes. And it turns out if you want to minimize the time spent searching for the files you use most often, LRU is mathematically optimal. Just putting a file back on top of the pile after you use it maintains this order naturally.
Does this relate to human memory, too?
The sources argue strongly that it does. Good memory isn't just about storing everything. It's about efficient retrieval, which means predicting what you're likely to need.
Like our brain has its own cache management.
Kind of. Research by Anderson and Schooler looked at how information fades in the real world, tracking things like New York Times headlines, baby name popularity, even people's email usage.
And they found patterns.
They found that the probability of something reappearing or being needed again decreased over time in a way that closely matched the classic Ebbinghaus forgetting curve from psychology. It suggests our memory systems might be optimized, like LRU, to keep recently accessed information more readily available.
So forgetting isn't just a flaw, it's maybe a feature, a way to manage the cache.
That's the implication. Caching highlights unavoidable trade-offs. You can't keep everything instantly accessible, whether it's library books, Amazon products, or facts in your head. Something has to be prioritized.
Okay, trade-offs in space lead us to trade-offs in time. Scheduling. We all struggle with this. Too much to do, not enough time.
Absolutely. And the tasks themselves have all sorts of complexities. Some depend on others, some have hard deadlines, some are urgent, some are important. Aristotle wasn't wrong. We are what we repeatedly do. Our schedule shapes us.
One simple strategy mentioned is earliest due date, EDD.
Right. If your main goal is to minimize the maximum lateness of any single task, basically, avoid having any one thing be incredibly late, then doing the task with the soonest deadline first is provably optimal.
Like eating the stuff from your CSA box that spoils quickest first.
Perfect example. But EDD might not be best for other goals. It might not minimize the total amount of spoilage, for instance, if you have one thing due very soon, but lots of other things that will spoil if left a bit longer.
What if the goal is just getting stuff done?
Right.
Reducing the backlog.
Then the sources introduce a different metric, minimizing the sum of completion times. Basically, minimizing the total waiting time experienced by everyone waiting for their task.
And how do you achieve that?
Interestingly, by prioritizing the shortest tasks first, shortest processing time, or SPT. If you have a one-day project and a four-day project, doing the one-day one first means one client waits 1 day and the other waits 5, 1 plus 4. Doing the four-day one first means one waits 4 days and the other waits 5, 4 plus 1. The total waiting time is lower with SPT.
That reminds me of the debt snowball method in personal finance.
Exactly. Paying off the smallest debts first gives quick psychological wins, even if paying off the highest interest debt first, like EDD for urgency, is mathematically better for minimizing total interest paid. Our goals influence the optimal strategy.
It's wild how even phone notifications, those little red badges, can subtly push us towards SPT.
Totally. You want to clear the easy emails just to make the number go down, even if they aren't the most important? The interface design nudges your scheduling metric.
But finding the perfect schedule for complex situations,
Yes,
that's hard, right?
Very hard. Lawler's research showed that for many realistic scheduling scenarios with various constraints, finding the truly optimal schedule is often intractable. Meaning, there's likely no efficient algorithm that can guarantee the best solution in a reasonable amount of time for large problems.
We also have to deal with the cost of switching tasks, context switching.
Yeah, that's a huge factor, especially for complex mental work like programming or writing. You have to load the whole state of the problem into your head. Short, interrupted blocks of time can be incredibly unproductive because you spend more time reloading context than doing work.
Like trying to juggle too many things at once.
Precisely. In computer multitasking, there's a phenomenon called thrashing. If the system tries to run too many processes concurrently, it can spend nearly all its time just switching between them, swapping memory, saving states, and get almost no actual work done. Throughput collapses.
So sometimes doing fewer things concurrently actually leads to getting more done overall.
It can, absolutely. Slowing down to reduce context switching can increase total throughput. Operating systems try to manage this by giving each program time slices within a period, but if too many programs are active, the overhead kills performance.
And these scheduling dilemmas pop up everywhere. When to do laundry, how far ahead to make plans.
It's constant. Understanding these principles, deadlines, task length, dependencies, context switching costs, gives us a much richer vocabulary for thinking about how we manage our own time.
Right. So moving from managing time to managing information scarcity. We hear about big data, but what about when you have very little data?
Yeah, often we have to make judgments based on just one or two examples. Small data is incredibly common in real life.
How can computer science principles help there? Bayes' rule comes up.
Bayes' rule is fundamental. It's a formal way to update our beliefs based on new evidence. You start with a prior belief, observe some data, and calculate a posterior belief. It lets you reason backward from effects to probable causes.
The raffle ticket example illustrates this. If you draw one winning ticket,
Bayes, or rather Richard Price, who analyzed Bayes' notes, showed that observing one win makes it significantly more likely that a large proportion of tickets are winners. But it doesn't directly give you a single expected value.
that was Laplace.
Yes, Laplace built on Bayes' work to give us a way to calculate that expectation, his law of succession. If you've seen W wins in n attempts, the expected probability of success on the next try, or the overall proportion, is W plus 1, n plus 2.
So one win out of one try, W1, N1, gives an expectation of 1 plus 1, 1 plus 2 equals 23.
Exactly. It incorporates the observation, but also accounts for the limited data by adding pseudo-counts.
Then there's the Copernican principle, the Berlin Wall example.
Right. Physicist J. Richard Gott visited the Berlin Wall and, knowing nothing else about its history, predicted its future lifespan based only on how long it had already existed when he saw it.
How does that work?
The principle assumes you're observing the phenomenon at a random point in its total lifespan. If that's true, the median expectation is that it will last as long into the future as it has already lasted into the past. So if it had been up for 8 years when he saw it, his best guess was it had about 8 years left.
And Harold Jeffreys had a similar idea for estimating tram numbers.
Yeah, based on seeing a single tram car with a serial number, say X, his reasoning suggested the best estimate for the total number of trams was roughly 2x. You assume you saw a randomly numbered tram.
But some things don't follow this pattern, right? They're memoryless.
Correct. Things that follow an Erlang or exponential distribution are memoryless. The probability of them ending in the next minute is constant, regardless of how long they've already been going on.
Like radioactive decay. Or maybe how long you wait for a bus.
Often, yes. Or intervals between calls at a call center, potentially even things like political terms in office. For these, knowing the past duration doesn't help predict the future duration.
So how are we often so good at making predictions from sparse data, if these rules are complex?
The argument is that we have incredibly rich priors. We've absorbed a vast amount of implicit knowledge about how long things typically last, how processes usually unfold. We have built-in expectations about movie lengths, lifespans, project durations, etc.
We're not starting from scratch with every observation.
Not at all. We leverage this huge internal database of world knowledge, often subconsciously.
This even reframes the marshmallow experiment.
It offers a different perspective, yeah. Maybe the kids who waited weren't just demonstrating raw willpower. Maybe they had learned from prior experience, their priors, that the experimenter was reliable and would actually deliver the second marshmallow. Their expectations, based on limited data perhaps, might have driven their ability to wait.
Fascinating. So using priors helps with little data. But what about the danger of seeing patterns that aren't there? Overfitting.
Yes, the flip side, overfitting is a huge issue in machine learning and arguably in human reasoning too. It's when your model becomes too complex and fits the noise in your specific data rather than the underlying signal,
So it matches the past data perfectly.
but makes terrible predictions about the future or for new data points. It hasn't generalized well.
Darwin's pro-con list for marriage is mentioned as a simple approach.
Yeah, a classic simple heuristic. Ben Franklin did something similar, listing pros and cons and even trying to assign rough weights. These avoid excessive complexity.
The life satisfaction example illustrates overfitting well.
Right. A simple model, like satisfaction declines steadily, might be broadly okay. A slightly more complex one, declines then levels off, might fit the data better. But a super complex 9-factor model might fit the initial data perfectly.
But then predict wildly unrealistic things long term, because it's capturing random fluctuations in that specific data set.
Exactly. It's a core lesson. More complexity is not always better. If there's noise or limited data, overly complex models can be brittle and make worse predictions than simple ones.
The overfitting fitness analogy is good too, focusing only on easily measured metrics like body fat.
Might lead you to unhealthy extremes because you're optimizing for an imperfect proxy, overfitting to the metric rather than the true goal of health.
How do we detect overfitting? Cross-validation.
That's a standard technique. You hold back some of your data, the test set. You build your model using the rest of the training set. Then you see how well your model performs on the data it hasn't seen before, the test set.
And if it does great on training, but poorly on testing.
That's a red flag for overfitting. The model hasn't learned the general pattern.
Are there ways to actively prevent it? The lasso?
Yes, the lasso, least absolute shrinkage and selection operator, is a technique that adds a penalty for model complexity. It forces the model to pay for adding more parameters or features, encouraging simply solutions that are less likely to overfit.
Nature kind of does this too, right?
Yeah.
Penalizes complexity.
You could argue that. Constraints like limited time, energy, memory, attention, they push biological systems towards solutions that are efficient and not overly complex unless the complexity provides a significant advantage. Think about the energy cost of the human brain.
Even language favors simplicity.
Often, yes. Concise explanations are easier to understand, remember, and transmit. There's a natural pressure against unnecessary jargon or complexity.
The story about Harry Markowitz, the Nobel laureate economist.
It's brilliant. He developed highly sophisticated mathematical portfolio optimization theory, but for his own retirement savings, he used a simple heuristic. Just diversify broadly.
Because the real world is too uncertain and noisy for the complex model.
Perhaps. Or maybe the simple heuristic gets you 90% of the way there with much less effort and risk of error. When uncertainty is high, broad strokes are often better than intricate detail, like entrepreneurs sketching ideas with a thick Sharpie first.
This connects to tackling really hard computational problems too, like the traveling salesman.
Yes, the traveling salesman problem, TSP, find the shortest route visiting N cities exactly once is famously hard. The number of possible routes grows factorially.
So finding the perfect solution is often impossible for large numbers of cities.
Right. But we have heuristics, good rules of thumb that find solutions very close to optimal very quickly.
Like the minimum spanning tree heuristic.
Exactly. Finding the minimum spanning tree, the shortest set of edges connecting all cities, is easy, and algorithms based on it can get within a small percentage of the optimal TSP tour length, even for thousands of cities.
So we approximate. Other techniques are mentioned too, like relaxation.
Yes, for discrete optimization problems where choices are distinct, like TSP or placing fire stations, continuous relaxation turns discrete choices into continuous variables, which can be easier to solve, giving an approximate answer. Lagrangian relaxation turns constraints into penalties you pay for violating them, kind of like a band deciding if paying the curfew fine is worth playing an encore.
Even finding prime numbers for cryptography uses clever tricks.
Definitely. The sieve of Eratosthenes works for small numbers, but for the huge primes needed in crypto, it's too slow. Probabilistic tests like Miller-Rabin use randomness to quickly determine if a number is highly likely to be prime, without absolute certainty, which is good enough for practical purposes.
And philosophical heuristics, Rawls' a veil of ignorance.
Yeah, a heuristic for designing fair rules. Imagine you don't know your own position in the society you're creating. It forces impartiality.
What about simulated annealing, inspired by metallurgy?
It's a neat optimization technique. You start with a potential solution and randomly explore nearby solutions. You allow some uphill moves to worse solutions initially, controlled by a temperature parameter that gradually decreases. This helps avoid getting stuck in suboptimal local peaks and find better overall solutions, used successfully for things like chip layout.
In Campbell's blind variation and selective retention, like evolution for ideas.
Basically, yes. Generate lots of ideas randomly, blind variation, then test them and keep the ones that work, selective retention. A fundamental process for creativity and learning.
The random Wikipedia clicking anecdote is fun too.
Just embracing randomness to get a better feel for the breadth of information and maybe better calibrate your sense of coincidence in life. It's clear that even for incredibly hard problems, computer science offers a rich toolbox, heuristics, approximation, randomization, penalties, ways to find good enough solutions when perfection is out of reach.
Okay, let's move to networks. How computers talk to each other and what that teaches us about human communication.
The internet itself is a giant case study. Its design principles have had to tackle challenges like reliability, congestion, and fairness, things we deal with constantly.
The core idea is packet switching, right? Not one continuous connection.
Exactly. Data gets broken into small packets, each individually addressed. They can travel different routes, maybe arrive out of order, and get reassembled at the destination. TCP, the transmission control protocol developed by Vint Cerf and Bob Kahn, manages this process.
And phone companies were initially skeptical.
Very. They were used to dedicated circuits. But packet switching's beauty is its flexibility. It can run over almost any underlying medium. Ethernet, Wi-Fi, fiber optics.
Even pigeons.
Yes, there was actually a famous satirical RFC, request for comments, proposing IP over avian carriers. It made the point about medium independence.
How does TCP ensure packets arrive? Acknowledgements, ACKs.
Right. The receiver sends back an ACK for data received. This confirms delivery. But these ACKs themselves generate traffic. Streaming Netflix, for example, involves a surprising amount of upstream traffic just for ACKs.
Kind of like conversational back channels, the and nods.
It's a great analogy. Those little signals confirm the communication channel is open and the message is being received, just like ACKs.
What happens when packets don't get through? When ACKs don't arrive?
TCP uses exponential backoff. If a packet seems lost, no ACK received, the sender waits a certain amount of time and retransmits. If that also fails, it waits twice as long before trying again, then 4 times, 8 times, and so on.
The waiting time increases exponentially.
Yes. It's a way to avoid overwhelming a potentially congested network by rapidly backing off.
And this has human parallels, like rebuilding trust.
The sources suggest it offers an interesting model. Maybe repeated violations require exponentially longer periods of demonstrated good behavior, sobriety, to restore trust. It allows for finite patience but infinite mercy, in a sense.
How does TCP handle congestion? Too much traffic.
Primarily through a mechanism called additive increase multiplicative decrease, or AMD.
Additive increase.
The sender slowly, linearly increases its sending rate, additive increase, as long as ACKs keep coming back smoothly.
Okay, testing the waters. Multiplicative decrease.
As soon as a packet is lost, signaling congestion, the sender drastically cuts its sending rate, often in half, multiplicative decrease. Then it starts slowly increasing again.
Creating that TCP sawtooth pattern you see on graphs.
Exactly. Gently probe for more bandwidth, but react aggressively to signs of trouble. It's like how a squirrel might cautiously approach dropped food scraps.
And AMD is seen as a fair way to share resources.
Generally, yes. It allows multiple connections to converge on a reasonably fair share of the available bandwidth over time without explicit coordination. Quite different from the Peter Principle idea, where people just rise to their level of incompetence in a hierarchy.
But there are still problems, like buffer bloat.
Ah, yes. Jim Geddes identified this issue. Network equipment manufacturers started putting huge memory buffers in routers and modems, thinking bigger is always better.
But it wasn't.
No. These massive buffers could absorb huge bursts of data without dropping packets immediately. But that meant packets could sit in the buffer for a long, long time before being sent, causing high latency or delay.
So you have high bandwidth, but things still feel sluggish because of the delay.
Precisely. Like a donut shop with a massive, slow-moving queue. The bakers might be fast, bandwidth, but the huge line, buffer, means you wait ages for your donut packet. This delay kills interactivity for things like video calls or online gaming.
How does TCP even know there's congestion if packets aren't being dropped right away?
That's the problem. The main signal TCP uses to slow down, multiplicative decrease, is packet loss. When buffers are huge, packets get delayed instead of dropped, so TCP keeps sending too fast for too long, filling up the buffer and causing latency. When the buffer finally fills completely, the router resorts to tail drop, just discarding new packets.
So tail drop is the harsh feedback mechanism.
Yes, and the sources playfully suggest maybe we need more tail drop in human systems sometimes. Instead of letting emails pile up into an infinitely long high latency queue, maybe auto-rejecting emails beyond a certain limit would be a more effective, albeit blunter, way to manage overload.
Interesting thought. And the focus on latency over just bandwidth.
Stuart Cheshire argued this powerfully. For human perception and interaction, low latency is often more critical than raw bandwidth. We need responsive systems. His analogy was, we need more Concords, low latency for the internet, not just bigger Boeing 747s high bandwidth.
It really shows how designing these communication protocols involves solving deep problems with broad relevance.
Feedback, fairness, managing delays, these are universal challenges.
All right, let's venture into maybe the trickiest territory, recursion. Thinking about thinking about thinking.
The Hall of Mirrors, where a problem or definition refers to itself, it can get complicated fast. The wine riddle from The Princess Bride is a perfect pop culture example.
The Zini trying to outthink the man in black.
Exactly. Thinking about what the other person knows you know they know, it spirals.
John Maynard Keynes applied this to investing.
He did. He famously described stock valuation not as guessing the true value, but as anticipating the anticipations of others. What do other people think the value will be? And what do they think other people will think? It's deeply recursive.
Poker seems like a prime example, too. The Tom Dwan bluff.
Oh yeah, a legendary hand. He bluffed huge with literally the worst possible starting hand, even telling his opponent what he had, playing on multiple levels of, what does he think I think he thinks?
So in poker, you need to be thinking ahead, but not too far ahead.
That's the tricky balance. You don't want to be predictable, level 1. But if you're operating on level 4 thinking, and your opponent is stuck on level 2, your clever play might go right over their head. Sometimes the goal is to trap them in a leveling war against themselves, making them overthink simple situations.
Game theory tries to formalize this with concepts like Nash equilibrium.
Right. A Nash equilibrium is a state in a game, like rock, paper, scissors, where no player can improve their outcome by changing only their own strategy, assuming everyone else stays the same. It's a stable point.
But finding these equilibrias in complex, real-world games
turns out to be computationally extremely hard, often intractable. This leads computer scientists like Papadimitriou and Aronson to question how relevant Nash equilibrium is as a predictor of actual behavior if rational players can't even calculate it.
The prisoner's dilemma is the classic example of where individual rationality leads to a bad collective outcome.
Right. Absolutely. Both prisoners are better off if they both stay silent and cooperate, but the individual incentive for each is to betray the other, defect, leading to a worse outcome for both.
This gap is called the price of anarchy.
Yes, the difference between the optimal cooperative outcome and the potentially much worse outcome of the selfish equilibrium. In the prisoner's dilemma, it can be terrible.
Hardin's Tragedy of the Commons is a real-world version.
Exactly. Shared resources, like fisheries or clean air. Individual incentive is to take as much as possible, leading to depletion or pollution that harms everyone. Leaded gasoline was a historical example. Climate change is the current, massive one.
And these bad equilibria can persist even when everyone knows they're bad, like Black Friday sales starting earlier and earlier.
Right. No single retailer wants to be the last one open, so competitive pressure drives them all to open ridiculously early, even if it's collectively suboptimal. Just changing the payoffs slightly might not even fix it.
The Evernote example, paying people to take vacation.
Yeah, it didn't solve the underlying competitive pressure to take less vacation than your peers if that's perceived as beneficial for your career within the company culture. The equilibrium didn't necessarily change.
So instead of just analyzing games, we can try to design them. Mechanism design.
Exactly. Design the rules and incentives to lead players towards a desired outcome. Our sources even suggest emotions, like outrage at unfairness or loyalty, can be seen as evolved mechanisms that help enforce cooperation or contracts without needing external police. They change the game's payoffs internally.
Auctions are another recursive headache.
Oh, definitely. Your bid depends on what you think others will bid, which depends on what they think you'll bid, especially in sealed bid or Dutch descending price auctions.
And that Amazon textbook pricing cascade, $23 million.
A truly bizarre example. Two sellers' automated pricing algorithms got locked into a recursive feedback loop, apparently based almost entirely on each other's prices, driving the price up astronomically. An extreme case of relying on others' behavior instead of intrinsic value.
So is navigating these recursive social loops always a nightmare?
The sources suggest it doesn't have to be. Sometimes adopting simpler strategies, refusing to get drawn into endless second-guessing, can be effective. Maybe the simplest strategy is the optimal one because it avoids the complexity trap.
Wow. So wrapping this all up, it feels like looking at life through this computational lens, applying these ideas from computer science. It really offers a different, powerful way to think about everyday challenges.
It really does. Optimal stopping, explore, exploit, sorting, caching, scheduling, dealing with limited data, avoiding overfitting, handling network effects, navigating recursive thinking. These aren't just abstract concepts, they're frameworks.
Frameworks for making sense of the choices and trade-offs we face constantly.
Exactly. And maybe by understanding these underlying human algorithms, the implicit rules we often follow, we can become a bit more intentional, maybe a bit more effective, perhaps even a bit less overwhelmed by it all.
So a final thought for everyone listening. Think about a decision you've grappled with recently. Could any of these ideas we discussed today, optimal stopping, explore, exploit, whatever, offer a new angle, a different insight?
And taking it a step further, in your interactions, how could you extend a little computational kindness? Maybe making things easier for others to process, being clear in communication, acknowledging limitations.
Lots to chew on there. This deep dive really highlights the surprising and fascinating connections between the logic of computers and the complexities of being human.
Absolutely. There's so much more to explore this intersection. Hopefully this gives everyone a starting point for thinking algorithmically about their own lives.